Now we present generating audio-visual synergy fluid animation for highly immersive VR experience. This research introduces an image-to-sound video framework that generates synchronized audio-visual fluid animations from a static image, aiming to enhance the immersive experience within VR environments. Our work addresses the image-to-sound video paradigm, transforming a single static image into a synchronized audio-visual fluid animation. This process bridges the gap between stillness and motion, significantly enhancing the sense of reality and presence required for immersive VR. This framework offers a broad application prospect. In VR tourism, it allows users to experience remote natural wonders. In digital therapy, it generates calming, synchronized environments, and in virtual production, it provides efficient tools for VFX artists to create complex natural dynamics. With the growing demand for immersion, static fluid images can no longer satisfy users' visual expectations. Thanks to the advancement of generative AI, it has become possible to generate fluid animations with synchronized audio and video from a single image, significantly enriching sensory experiences. At the same time, the popularity of VR technology has accelerated the application of fluid animation in virtual environments. The current trend is further extending toward audiovisual collaborative fluid animation generation to achieve a more comprehensive immersive experience. However, generating high-quality joint audio and video for fluid phenomena in VR still faces challenges. First, the dynamic realism of video textures is absolutely essential for maintaining immersion, yet, many existing methods still suffer from limitations in maintaining physical consistency and texture authenticity. Second, audiovisual alignment is equally critical for realism. Current approaches often encounter issues like audiovisual misalignment or abrupt scene transitions, which fail to meet the high standards required for deep immersion in dynamic VR scenarios. To address these issues, we propose an audiovisual synergistic fluid animation generation framework from a single image, which enhances audiovisual immersion in VR by improving texture fidelity and audiovisual consistency. This framework consists of the Detail-Enhanced Texture Generator and the Physics-Guided Audio Generator. Detail-Enhanced Texture Generator exploits the global local physics guidance and temporal texture modeling to improve video textures with rich dynamic details. Physics-Guided Audio Generator incorporates static visual semantics and dynamic rhythm semantics to optimize audiovisual synchronization. In Detail-Enhanced Texture Generator, the input image is encoded through a transformer-based encoder to extract features. Combined with Z-layer for linear weighting, prompts and image preprocessing are used to obtain motion and depth, which are then guided by global local physics to generate pre-motion. Subsequently, high-fidelity warped features are produced by carefully integrating global and local warp operations to preserve fine-grained details. Temporal texture modeling further refines this process by extracting adjacent features and assigned cumulative interframe differences. This modeling is reinforced by a two-stage cross-attention mechanism with the reference frame to strengthen temporal associations. The texture decoder then leverages these enhanced cues to generate high-quality, dynamically consistent frames. Meanwhile, these warped features and pre-motion data are utilized as critical inputs for the physics-guided audio generator to facilitate and guide the subsequent sound generation process. The physics-guided audio generator focuses on achieving a tight coupling between visual motion and auditory output. It extracts essential semantic information from the warped features and pre-motion, effectively enhancing both static and dynamic features via cross-attention. Specifically, it utilizes a Visual Semantic Augmenter and a Rhythm Semantic Adapter to model the scene in rhythm. These enhanced multimodal features are then fused with the audio latents through an attention mechanism, resulting in the generation of highly synchronized audio that matches the scene's semantic content and physical rhythm. In summary, by integrating the detail-enhanced texture generator with the physics-guided audio generator, our framework provides a cohesive methodology for producing high-fidelity fluid animations. This synergistic approach ensures that both visual dynamics and auditory effects remain physically consistent, collectively elevating the immersive experience in virtual reality. Regarding quantitative results, we evaluated our framework on 2 datasets against several representative methods, as shown in the table. Our approach consistently achieves the best performance across all core metrics. Specifically, the improved FVD and KVD scores demonstrate superior texture realism provided by our DET module, while the AV-Align and ABVIA results confirm that the PGA module effectively optimizes audio-visual synchronization. These findings validate the effectiveness of our proposed synergistic framework. To further validate our method's effectiveness, we visualized the generated results in VR and compared them with Dreamina and Yuan. Comparison reveals that both competing methods exhibit noticeable audio-visual misalignment. For example, the Yuan method often produces abrupt video transitions, which disrupts the user's immersion. In contrast, our method maintains excellent video stability and generates periodic, realistic ocean wave-like sounds. These visual and auditory details demonstrate that our framework effectively enhances the consistency and physical plausibility of the animation. To evaluate actual user perception, we conducted a comprehensive user study involving 30 participants with diverse backgrounds. We evaluated the content across both desktop and VR environments. We utilized 5 subjective metrics: immersion, physical plausibility, texture realism, audio quality, and audio-visual consistency. The results show that our method consistently achieves the highest mean scores across all metrics in both viewing conditions. This confirms that our framework provides a superior and more engaging user experience. To ensure the validity of these evaluations, we performed a statistical reliability analysis using Kendall's coefficient of concordance. Our analysis shows that all calculated chi-square values are significantly higher than the critical threshold of 5.991. This indicates a statistically significant agreement among the evaluators across all dimensions and environments. These findings substantiate the reliability and consistency of our subjective results, confirming that our method provides a robustly superior user experience. Regarding limitations, we acknowledge that extreme lighting conditions can cause audio synchronization errors due to cascading dependencies between modules. Additionally, our current framework shows limited generalization to diverse fluid categories beyond common water scenes. Regarding these issues, our future work will focus on integrating physics-based synthesis directly into audio generation to mitigate model degradation. Furthermore, we aim to generalize the framework to broader fluid types by incorporating category-specific physics priors. In conclusion, we have presented an audio-visual synergistic framework that effectively generates high-fidelity fluid animations for immersive VR environments. By integrating our detail-enhanced texture generator and physics-guided audio generator, our approach achieves superior performance in both texture realism and temporal synchronization. While this work provides some initial insights, we recognize that certain limitations remain and have established a direction for further optimization. That concludes our presentation. We would like to express our sincere gratitude to IEVR for providing this opportunity to share our research. Please do not hesitate to contact us if you have any questions. Thank you for your attention.